All right, today we're going to be going over some generic derivatives. So our objective for today is just to figure out what in the world a generic derivative is and just some general tips on knowing how to remember or figure out or crack or whatever these generic derivatives. Okay, so let's get started here. So don't really overthink a generic derivative. It's really just a derivative that you should know off the bat, you should know cold, and requires little to no analytic work. So the generic derivative sheet that you received, some of the problems in that sheet are not really generic, but I wouldn't ignore them because they could show up on other parts of your exam. So just FYI, the problems that I am going to go over today are actual just generic derivatives fully. Okay, these are derivatives that fall under the branch of generic, in my opinion. So let's start off here with the first one. So we have y equals to f of g of u, and we need to find dy dx. So in other words, we need to take the derivative with respect to x on both sides. So this may look a bit confusing at first, but this is actually just generalizing something that you could do in 5 seconds. How so? Let's have a bit of a side problem here. So let's say y equals to, 3x plus 5 cubed. Okay? So you could do the derivative of this really easily, right? Dy dx is just 3 times 3x plus 5 squared. Take the derivative of the inside, and that's just 3. And so this is our answer. It's essentially the same thing here. Right? If we view this as a composition of functions here, we can let f of x equal to x cubed, right? Cubed. And then g of x equal to 3x plus 5. Because if we do then f of g of x, that's the same as f of 3x plus 5. And then remember, if f of x is x cubed, f of 3x plus 5 is 3x plus 5 cubed. Wait a minute, that's the same as this. So I am modeling y as a composition of functions here. And so really the chain rule is a way of taking the derivative of composition of functions. And what this is doing is generalizing it. Generic. It's a generic way of expressing the chain rule. So dy dx in this case would just be f prime of g of u times g prime of u. And remember, since this is in terms of u, we need to do the chain rule once again because, we're taking the derivative with respect to x, so this will be times du dx. Now, FYI, right? How do you know this, right? For your information, this is how I got it, right? Think about this. F prime, what is f prime? F prime is 3x squared, 3x squared. And this is the something, right? G of u is, g of x, right? 3x plus 5. So f prime of this, and then times the derivative of this, which is 3. And then the reason why we have the du dx here is because another part of chain rule, because we're taking the derivative with respect to x, not with respect to u. All right, hopefully that kind of makes sense, right? It's just generalizing, right? I'm going to write this here. Generalizing the chain rule. That's all this is. Okay, and when you take AP Calculus next year, they will ask you a lot of questions regarding this general form of the chain rule. So make sure you know this. Okay, so now y equals the absolute value of u. There are 2 ways of kind of dealing with this here. The first is just thinking about it, right? Let's actually sketch the graph of this. Here, let's do this over here. Let's sketch the graph here. This is what your absolute value should look like, right? Let's think about absolute value of x, right? Let's think about the slope here. So, of course, first thing, right? Sharp turn here, sharp turn. So the slope is undefined here. But then to the right, of 0, the slope is positive 1. And to the left of 0, the slope is negative 1. Can we think of a function which kind of models this, right? Because remember, the derivative is like the slope function. It's the function that outputs slope at a particular point of that original function. So, hint, you studied this in limits unit. Think about this. We have positive 1 here, negative 1 here, undefined at 0. This kind of looks like the function y equals to absolute value of x over x, doesn't it? Or if you were thinking y equals to x over absolute value of x, you'd also be correct because these are the exact same functions. This perfectly models the output, right, the slope at each point of absolute value of x, right? If we think about 0 here, think about 0, it's undefined. If we think about, to the right of 0, if we think about, 3, it's just going to be 1. If we think about negative 3, it's just going to be negative 1, right? Perfectly models this. Now, if this kind of doesn't really make sense, hopefully it should. Think about how can we represent the absolute value of x in another way. Well, another way would just be thinking about the absolute value of x equals to the square root of x squared. Okay? So we can then take the derivative, right? We can rewrite this as x squared to the 1/2. We can take the derivative of this, right? So if we let, f of x equal to x squared to the 1/2, we can then do power rule, right? F prime of x equals to 1/2 times x squared to the 1/2 minus 1 times the derivative of the inside here, which is just 2x. And then what we'll get here, the 2's will cancel. And then we get x times x squared to the negative 1/2. Okay, so I'm going to put this in the denominator here as x over x squared to the 1/2. Remember, then this is just the same as x over the square root of x squared. Remember, the square root of x squared is just absolute value of x, so then this will just be then x over absolute value of x. So two ways of kind of thinking about this. So in this case, the derivative would just be, y prime is just absolute value of u over u times du dx, right? Because taking the derivative with respect to x, so we have to add that additional chain rule, so du dx. Okay, now just, quick FYI here, right? So remember, I said that absolute value of u is the same as, absolute value of u over u is the same as u over absolute value of u. Here's a way, like, to quickly, just clarify, right? If we do, times absolute value of u in the numerator, or the denominator in the numerator, right, this will then be u absolute value of u. And remember, absolute value always yields a positive output. So a positive times a positive should be another positive. So we could rewrite it as absolute value of u squared, but remember, anything squared is positive, so this will just be the same as u squared. This will cancel out. This will become a 1, and we get absolute value of u over u, which is the same as this. Okay, so just to clarify, just another FYI. Okay, now these are just your trig derivatives here. I think the best advice is if you know your sine and you know your cosine, you could figure the rest of these out. So this would just be, right, y prime is just cosine of u times du dx. This would then, y prime is negative sine of u times du dx. And then remember, with tangent, again, I expect, I would say that you guys should just know these cold. But if you're really stuck, okay, just think about, right, sine of u over cosine of u. You do the quotient rule. Here, I don't know, like a 1 over sine of u quotient rule, 1 over cosine of u quotient rule, cosine of u over sine of u, something like that. If you're really stuck, But I would say at this point you should just know these, cold, right? So tangent of u, that would just be, y prime is just secant squared of u times du dx. And then here, y prime equals to negative cosecant of u cotangent of u times du dx. Here, this would be y prime equals to secant of u tangent of u times du dx. And then here, here, y prime is just negative cosecant squared of u times du dx. Another good piece of advice is the co-derivatives, right, like cosine, cosecant, cotangent, right? These all are the negative derivatives, okay? So another good way of just remembering these. Okay, this is a product rule. I hope you guys know this. If you really don't know product rule, a quick trick here is just take the natural log of both sides and then just do log differentiation. Right, this would be ln of f of u, ln of g of u. Take the derivative with respect to x of both sides, like 1 over y dy dx equals to 1 over f of u times f prime of u. Keep going from there, but you should know the product rule, right? I would expect you to just know the product rule, right? So y prime would just be right times the derivative of the left. Now remember, this is du dx plus the right, the left. Sorry, I meant to say. Sorry. This should be the y prime is the left times the derivative of the right, and then du dx plus the right times the derivative of the left times then du dx. We can then factor out here just the du dx. We can rewrite it as like f of u times g prime of u plus g of u times f prime of u, all of that times du dx, and that would also be fine. And then here is just a quotient rule, right? Again, you could, if you're really stuck, but I really wouldn't expect you guys to be stuck, right? Just, it's quotient rule, but log differentiation is a way of getting it, right? Just do bottom, right? Y prime equals to bottom times the derivative of the top. And remember, this is du dx minus top times the derivative of the bottom, du dx, all over, it's better, all over bottom squared. We can once again factor out the du dx here and rewrite it as g of u times f prime of u minus f of u times g prime of u over g of u squared, and that all times du dx. That is also fine. Okay, and then here this is just log of natural log, right? If y equals ln of x, right, dy dx, or let's say ln of u in this case, ln of u dy dx equals to just 1 over u times du dx, right? This is, remember, ln of u equals to log base e of u. So then what about bases other than e, right? Log base e of u. Well, what about other bases besides e? Well, here we can just use the change of base formula. Again, I'd highly suggest you just know this. You have been expected to know this in the past, and I would say you should still, I would expect you to still know this cold. But still, if you're really stuck, just do a change of base here, right? We could just do, this is the same as log of, we could say log base e, right? You can change it to any base. So log base e of u over log base e of a. Now, one thing to keep in mind here is that this log base e of a is actually a constant, right? Because we're assuming the base is a constant. So I'm going to do then, you can do dy dx. We can actually factor out this 1 over, we can say ln of a, because log base e ln dy dx, and then ddx of log base e of u, right? This is the same as 1 over ln of a times ddx of ln of u, right? Because log base e of u is the same as ln of u. And then this will then just be 1 over ln of a times 1 over u times du dx. So then here it'll just be 1 over u ln of a times du dx. Okay, so quick way of just getting the derivative of log of any base using the change of base formula. And yeah, just going here, remember y prime, just 1 over u times ln of, or 1 over u times du dx. Really, you should know that. There is a way of getting this through the derivative of e to the x, but just got to assume you know that. Here, a to the u, here a, just some constant, u is just a variable, so this will just be y prime equals to a to the u times ln of a times du dx. Nothing really special here. I'd expect you to know this also. There are ways of proving this too, but still, should know this. And then here, just a simple one power rule, right? We can rewrite this as u to the 1/2. So then y prime then equal to 1/2 u to the 1/2 minus 1 times du dx, otherwise known as 1 over 2 root u times du dx. Okay, so hopefully this video was helpful. Don't overthink this. You're going to do great. You don't need a good luck from me because, you're all going to do great. All right? Hopefully this helps.